Let's solve another problems related to momentum chapter. A hockey puck B rests on frictionless level ice and is struck by a second puck A, which was originally traveled at 40 meters per second and which is deflected 30 degrees from its original direction. Okay, so then they provide us a figure. There's a hockey puck B rests on frictionless. Okay, so it gives us the initial velocity of B. Rest means that it should be 0 at first. Yep. And then it's struck by the second puck A, boom, here. And then collisions occurs here. Okay, so there's some collisions again. And it also have an initial speed. Oh, that's really fast, like 40 meters per second. And then after that, they provided the final velocity direction of puck A and also puck B. Okay, puck B acquires a velocity at a 45 angle to the original direction of A. Okay, so then we see that the original directions of A is just the horizontal direction in this figure. The pucks have the same mass. Okay, compute the speed of each puck after the collision. Okay, so they ask us to find the speed final after the collisions. And B, what fractions of the original kinetic energy of puck A dissipates during the collision. So this is a collision, but it's not perfectly elastic because some kinetic energy have been lost. That's transferred to thermal heat for sure during the collision. So whenever we see collision, we see that, oh yeah, we can apply the momentum conservation, which says that the total momentum before the collisions will equals to the total momentum after the collisions. Nothing changed in the momentum, but not in the energy. It depends if it's whether it's a elastic collisions or an inelastic collision. And in here we can see that this is the directions of it. This is like 30 degrees north of the east, and this is like south of the east if we want to describe the directions of each vector. Okay, interesting. So what do you think? Well, I guess if we want to determine the speed, we could need to apply this one, right? Because momentum will have to do with the v by momentum equals to mv, yeah? And then if we want to determine the magnitude of the v, then that should be the speed. The magnitude of the velocity is the speed. What interesting here is that we just don't have on the velocity in one directions, but in different directions. So I guess that we have to analyze them, right, into the horizontal components and vertical components. Like that's the most simplest way to choose. You can choose in any directions that you want to analyze them, but the easiest one is the horizontal one and the vertical one. And just one thing as a hint for you is that whenever you have the collisions, the momentum is conserved, then it means that all the horizontal components can be conserved and all the vertical components can be conserved as well, which means that if the horizontal of the momentum, the net momentum here, that will be equals to the horizontal component, the net of the horizontal component of this one, and the plus with the horizontal component of this one. So try it. That's what I'm thinking, because if we want to calculate the speed of each puck, we should need at least like two equations, because we solve for like two variables. So we should need at least two equations to solve for two variables, which is the speed of A and the speed of B after the collision. And I think that once we got the V, then we can easily calculate the kinetic energy, right? Because it's just like 1/2 mv squared, and then we can compare the difference between the before and the after collisions. Okay, so try and think how to apply this one on each components, and then see you in the next video to see how we can solve it in details. Okay, thank you. Good luck.